So today our case history is the Hoover Dam. And then we'll finish compaction. They'll be short. And then we'll start talking about the flow of water through soil. So let me get the lights and we'll talk about the Hoover Dam. So the Hoover Dam was built between 1931 and 1935. And Herbert Hoover was the president at the time, and you remember 1929 was the Great Depression, and so the idea of building the dam was to give work and to try to improve the economy. And here are the credits, number of websites that used. And here's the location of the dam. So let me get the mouse pointer option, laser. All right. So here's the dam. This is the Colorado River. And the Colorado River goes here to the Grand Canyon. I mean, it's coming from the Grand Canyon, flowing this way, coming down and going down all the way to the Gulf of California in Mexico. So the dam is located right here, and for a long time, the bridge, I think, was built, some 10 years ago or so, and before you had to go down with your car and travel this way to go to the other side to Las Vegas. And then the bridge was built and made traffic a lot easier. So the dam is an arch dam. You can see it here. You know, we have two types of dams. I think I mentioned it before. Arch dams when the valley is narrow and the canyon is pretty deep, and the dam arches and gathers support from either side of the mountain and the canyon. And so that was the case. You can see here that the dam is here, and the spillway is upstream and spills to the side. And here is the spillway right here, and the dam is there. The water is flowing in this direction. A few things, the height is 221 meters. Remember the Teton Dam, which is the other dam that we've discussed, was 100 meters. So this one is 2 times higher. The length is relatively, as I said, is fairly narrow, 379. The width at the crest is about 14 meters. You have a road that goes over the top. But at the base, it's 200 meters. So this is the cross section here, very wide at the top and fairly narrow at, very wide at the bottom and narrow at the top. Volume of concrete, about 3 million cubic meters. And then the spillway that's right here is a drum gate spillway. So this is a huge undertaking, as you can imagine. 6 companies, 6 construction firms were selected. 5,000 people worked during peak time for the construction for about 5 years. The dam is named after President Hoover. Before that, it was called Boulder Dam because the entire city of Boulder was constructed for the workers, and at the time it was the largest man-made reservoir in the U.S. This is the site geology. So the valley of the Colorado River is fairly narrow and deep. Breccia is the type of rock that is found at the location. Dense reddish unit composed of fragment of monzonitic porphyry covered by another type of breccia. The bottom of the river alluvium, obviously, and they had to be removed. But the first thing when you have to construct a dam is you need to divert the river. You need to make sure you can work in the dry. So there was a lot of work tunneling through the side of the canyon to allow the Colorado River to go sideways so that the dam side could be dried up and the workers could work. So this is before the diversion of the Colorado River. Then the Colorado River is diverted. You will see it goes on tunnels on either side. And then the quay is built. And then the dam is being built. So this spans from 1931 to 1935. Engineering challenges, you have to divert the Colorado River, so that means you got to drill the tunnels. You have to remove the loose material and the canyon walls and the bottom, and there's mass concreting that has to take place. So let's look first at the diversion of the Colorado River. So let me show you this. So you're looking here, here's the dam as it's going to be built. The Colorado River is flowing in this direction. And you have to build these tunnels to bypass the flow. You see 1, 2, 3, 4, those 4 blue tunnels that will be used to bypass. You have an upper cofferdam to block the river, so that and a downstream barrier as well, so that now the dam site is dry and you can start working on the construction itself. Here are in cross section, you can see the 1, 2, 3 tunnels on this side, 1, 2, 3 tunnels on this side to handle the flow of the river. Here is the diversion of the river. You can see the river is now going this way, and this is being pumped dry so that work can start. And then this is the tunnels that are being built. And you remember when we talked about the Euro tunnel, I showed you some very large tunnel boring machine, TBMs. Well, at the time, 1931, you don't have those sorts of machines. And this is essentially the tunnel boring machine with the scaffolding and the people actually drilling the rock. So here is the tunneling machine in place. And so you advance very slowly compared to the Euro tunnel. But in the end, you have this big tunnel that's being constructed. You remove the loose material in the canyon wall because the dam is going to actually bear on the canyon walls for support, for resisting the push from the water. Here's some of the images. Mass concreting, 3.2 million cubic yards of concrete. Pouring ended in May 1935. It's done in lifts. You can see the buckets bringing the concrete. And this is starting foundation. Here are the different cells where the concrete is being poured. You can see them here. The cells are being concreted, and the dam is going up. Here's more of those same pictures. The amount of concrete is huge. Now, there were some problems associated with seepage and water pressure. Earthquake and settlement were 2 other considerations. I'll show you one bit of information on the uplift pressures that developed. Soon after the construction, there were some high uplift pressures generated by the water that began developing due to seepage underneath the right center of the dam. And the red line here shows you the pressures that were measured. And so the foundation was, the grouting took place to try to repair or improve the foundation, and this is the the limit of the additional grouting that was done to be able to slow down the water and to decrease the pressure. And the blue line is the pressure. So the vertical axis is water pressure, and horizontal axis is the distance along the dam. You can see the additional grouting decrease the pressure from the red line to the blue line. So that was successful. Now there are some negative effects when you build a dam. You lower the riverbed because the water is, the weight of the dam, number one, and the water can increase in velocity downstream. You alter the quality of the water because you're storing it, and when you destroy the ecosystem and you increase evaporation. So all these things are part of the process, and obviously the advantages have to outweigh significantly the drawbacks. But it is a beautiful dam, and I'll finish with a few pictures of the dam. And then the bridge, as I said, the bridge was built much more recently, and now when you cross from here to there, you can watch, well, you got to watch the road first, but at least your passengers can watch the dam on the right-hand side when you go to Las Vegas in this direction. So that was the Hoover Dam. Let me put the lights back on, and then we'll get back to our business here. So I wanted to finish first the topic of compaction, because one of the things well, there's two topics left. So I'm still in compaction, soil compaction. And I showed you last time the laboratory test that is being done, the Proctor test that's being done to measure the maximum dry unit weight and the corresponding optimum moisture content. And then after this, once you have this information, you write in a specification that the job has to be done by reaching a high percentage of the maximum dry unit weight at within close proximity of the optimum moisture content. And but after that, you need to verify that this has been achieved. So there is field measurements associated with we'll call it field verification. So how do we do that? Well, most commonly we do that with a tool called the nuclear density device. And this device is about the size of a box, and you push into the material a rod that can go up to about 15 centimeters approximately. And then this rod is, there is an emission of nuclear rays that is being recorded by a receiver, and the density is calibrated to the number of the count of rays that are being received. In other words, if the material is very dense, then the rays will bounce back and forth and will not get to the receiver. And this tool is used to obtain gamma D and W. So that's how you verify that you have obtained what is necessary in the field. The other thing that I wanted to mention before we leave the topic of compaction was that there is a trend today to go towards verification and compaction control based on the soil modulus, the soil stiffness. In essence, one big application of compaction is pavements and roadways. Another application is dams and embankments and so on. But in the case of pavements, you want to make sure you have something that's very stiff so that when the big trucks go by, they don't sink into the material. So you limit, so the key is the stiffness or the modulus of the material. So there is a trend towards modulus-based compaction control. And I wanted to discuss this here. And when you do that, you can do that with various instruments. We've developed some here at ENM. You can then plot as you do with the Proctor test, the dry density versus the water content. So that's what we did last time. We have water content here. One thing I wanted to point out when I drew that bell-shaped curve, you remember the bell-shaped curve that is obtained from the test, the Proctor test. Then that bell-shaped curve has this pronounced shape because we don't plot gamma D from 0 to 20, let's say. We zoom in and we plot it from 18 to 21, let's say. So we emphasize the shape of that curve, but if we plot it from 0 to, say, 20, and this is going to be in kilonewton per cubic meter, then if we do that, you would see that the plot itself would be quite shallow. But if I do it from 18 to 20, and 18 goes here, then this plot will become much more pronounced. So that's gamma D. If, on the other side, I also plot the modulus. And so the modulus, and we'll come back to modulus and deformation of soil later on in the course, but the modulus would be in kilonewton per square meter. And modulus is a measure of stiffness of the material. If you did that, you would find that the curve is quite a bit different, and the peak may not be the same, but certainly the modulus drops down much more than the density when you're on the wet side of this optimum moisture content. Remember that here you have, I'll put it in red for the dry density, here you have the maximum, remember this one from last time, this is gamma D max, and this is W optimum moisture content. Okay? If you do the modulus, you're going to have an E max, and you're going to have another W optimum. They don't necessarily correspond. This is the future. You might see this, 10, 20 years from now. Right now, we're working with gamma D max. So concentrate on this thing, but be aware of the fact that in my mind, it makes more sense to measure the modulus than the dry density, because the modulus is what we use in the calculation, so it makes sense that if we use a certain number, when we come to the field, we want to verify that the number we use in the calculation is going to be verified in the field. So this is the trend for the future. All right. So that concludes our discussion on the compaction. Now I need to turn to a different topic, which is flow of water through soil. And so far in the class, you know, we've looked at the soil, what it's made of. We've looked at the grain, we've zoomed in to try to understand what they're made of inside the grains. Then we looked at index tests, you know, simple tests like water content, unit weight, and then Atterberg limits, grain size, tests that would lead to classification of the soil material. Now we're moving into a different topic, which is flow of water through soil. After flow of water through soil, we'll still have to discuss shear strength and then deformation, and we'll be done. Okay, so we're in the second major topic of the class. So let me write this up here. And the title is Flow of Water Through Soil. So one of the big applications of flow of water through soil is dams, particularly earth dams, because one of the first things to understand is that all soils are permeable, more or less. You can imagine that in clay, it's going to be hard for the water, it's going to take time for the water to go through the clay, compared to gravel, where it's going to be a lot easier for the water to go through the gravel. So, but the first thing is that all soils are pervious. All soils are pervious. More or less, but all soils are pervious. And basically to solve these types of problems, be it flow of water through soil, strength and deformation problems, we always have two sets of laws, two sets of rules, two sets of equations. The first set is fundamental equations. They're equations that are valid no matter what kind of material you deal with. You know, soil, steel, concrete, marshmallow, whatever, they're always valid. Fundamental equation. An example, equilibrium. The second set of laws that we have that are available to us are constitutive laws. And these are the ones that describe how the material behaves when you load it, for example. So they're elasticity, plasticity, viscoelasticity. These are all laws that describe how the material behaves. Flow of water through soil is no exception. And we basically have two major laws, major equations. The first one is conservation of mass. Conservation of mass. So that's a fundamental law. And this fundamental law is expressed by saying Q equals VA. And we'll come back to this in a minute. The second one is Darcy's law. And this one is expressed by V equals Ki. This is a constitutive law because K is a soil property. In there, there's no soil properties. It's whatever comes in has to go out. Q equals V. So I'm going to discuss those one by one. And let me start with Q equals VA. So that's something you've seen in hydraulics. The flow is equal to the velocity times the cross-section area. And in soils, when we write Q equals VA, if you think of a tube made of soil, so you have the soil tube. This soil tube has grains in it. If I chop it across, then I'm going to see some particles here. And the total area is going to be so first of all, I have the area of the voids, right? And the water can only go through the voids. It cannot go through the particles. So the blue one here, we'll call this A voids. And we've seen volume of voids and all that stuff, okay? This is a void. At the same time, let me use maybe the green pen just occasionally. If I use the entire cross-section here, then that's going to be A total. Okay? So the question is, what A should we put in there? Well, you can put either one of them, but you're not going to get the same velocity. So this is going to be equal to V seepage times AV, or V discharge times A total. So if you look at it from this point of view, V seepage is when you think of the water going through the voids, and that's what truly happens. So if you decide to ride a water molecule and you saw the speed measurements, you would actually see Vs. So that's the true speed of the water. But AV is not easy to evaluate. And so we favor V discharge times A total. So we're going to, from this point on, we're going to do V discharge A total. We're not going to use that, even though that might be more theoretically satisfying. It's another case where we do something wrong, but we do it consistently wrong so we can get back on our feet. So the first equation then, right here, is going to be Q equals V discharge A total. All right? First equation. And I can tell you, if in the midterm you get a problem on seepage, then the first reaction is to write Q equals VA, and then the second one, V equals KI. And we're going to discuss that V equals KI next. But before I can explain, and again, this V right there will be V discharge, because that's the one we're going to be using from this point on. But before I can talk about Darcy's law in more detail, I need to go through a few definitions. So let me erase this. Right here. And I want to go back. I want to go back to the Teton Dam. I want to make a cross section of the Teton Dam, and we're going to work all our definitions on that example, because hopefully it's still, you know, that's the dam where you had a leak on the right abutment, and the leak regressed, started to attack the downstream slope, bigger hole, and then finally the dam bridge. So this is definitely a seepage issue. So Teton Dam looks like this. Now we're going to simplify the cross section, and we're going to make the dam look like that, 100 meter high, and here's the dam. Behind the dam, we have to retain water. So we have water right here, and then you have, so typically we'll have a filter in the downstream so we can keep the water to seep through the inside of the dam. The problem is that if you have an exit of the water on the downstream phase, that's the beginning of the end. All right? You want to keep, so typically when you build a dam, we'll build a filter blanket here. So we can force the water to go through the dam and be captured in that drainage blanket and then come down, and the river keeps going here downstream. All right, so first definition, we're going to talk about energy, water energy. Well, let me put, let's say that we have an impervious layer at some depth here, because that's going to become useful. You don't have to have it, but it's a useful concept. So the first thing is, let's talk about energy. And we discuss energy in terms of water head. Now we're going to write that the total head is equal to the elevation head plus the pressure head plus the velocity head. So that's, if you have energy and you want to drive somewhere, you're going to burn energy through elevation, pressure, and velocity. In soils, the water goes very slowly. You will see that we're talking about a fraction of centimeters per second. And so it's going very slowly. So we don't lose much in terms of velocity. We don't lose much energy in terms of velocity. So we're going to ignore this part right here. We're going to set this one equal to 0. So the first thing to remember is that the total head is the elevation head plus the pressure head. So let's define each one of those. H sub E, as I said, is elevation head. Now this one is simply elevation above a chosen datum, 0 elevation. And you can choose whatever you want, but you have to be consistent. Once you choose it, that's the one that's going to be used for the entire problem. So if the water flows, and we'll see how to do this later, if the water flows something like this through the dam, so it goes like that, it goes underneath, and it ends up right there. So let's say that I pick a point randomly. I pick a point randomly inside the dam. I'll call it point M. And I choose a datum right here. That's going to be 0. So then the elevation head at M is simply going to be this distance. Okay? That's H sub E at M, elevation head. So that's easy. And when you start the problems, always start with elevation head, because that's an easy one. You can drop some points and be happy. The second one is the pressure head. The pressure head, so it's called pressure head. And the pressure head is equal to the pressure in the water. So you're at M now. You're right in the middle of the dam, and there's water there, and the water is under pressure. That pressure, if you have a pressure gauge, you can measure it, and it gives you UW. The pressure head is UW divided by gamma W. So if you do HP times gamma W, that gives you UW. So the pressure head, and you know if you have a container and the water is at this level at the bottom of the container, then the pressure is the height to the free water level times the unit weight of water. So if you were to drill, and that's not a good idea in that, but imagine that you have this imaginary pipe that comes down to M, like this. And you connect that pipe to M. Because of the pressure at M, the water is going to rise in the pipe. Where is it going to rise? Well, it's going to rise to a height equal to the pressure head. So the water may rise, let's see, I would say about here somewhere. Okay? And we were going to find out how to find this, where the water rises. It's not that simple, but that's my guess. So right here, this would be HP at M. So it's equal to UW over gamma W, and it is the height at which the water would rise in a pipe connected to M. And you might have guessed, if I had asked you, well, here's M, where does the water rise? You might say, oh, it's going to rise up to here. That's true if the water is not moving. If you're in a lake, so if I go here and I take a point A, right there. Okay, this is A. What is the elevation head at A? Well, height above data, right? That's the elevation head at A. What is the pressure head at A? Because the water is there, and the water is not moving, it's a big lake like behind the Hoover Dam, then this would be the pressure head at A, and this would be the elevation head at A. Okay? And that's to the water level because the water is not moving here. But here the water is moving. So you cannot make that same assumption. You have to find a way to determine that pressure head in another fashion. And then the total head is simply the elevation head plus the pressure head. Okay? In the problems that we're going to go through, because we need to solve the seepage problem, we need to be able to find what this H sub P is everywhere in the dam. Why? Because once you have H sub P, you got UW. And once you've got UW, you can calculate the effective stress. And once you have the effective stress, you can calculate the shear strength, as we will talk about later in the course. So that's why it's so important to be able to get this H sub P. So in the problems here, one, you start with the elevation head, H sub E. Two, you calculate the total head. And you do that using flow nets. All right, so that's another magic thing that we're going to discuss later on. But we calculate H sub T through the concept of flow nets. And then three, you get H sub P by difference between H sub T and H sub E. Okay? So I'm trying to give you some step-by-step consistent procedures. This is for the pressure head. We've seen these procedures for getting the profiles of effective stress. We've seen those procedures for solving the phase diagram problems, 1, 2, 3, and they're in my mind the best way to approach these types of problems. Okay, so these are very important definitions of total head, elevation head, and pressure head. All right. The second thing I need to define is the hydraulic gradient. So here we're talking about hydraulic gradient. symbol is I. The gradient is defined as the total head at A minus the total head at B divided by the drainage length from A to B. That's the definition. So it's a gradient, it's a slope if you wish, and this is energy. So what this gradient tells you is how much energy did you use to go from A to B, normalized with respect to the distance. It's very similar to a gas consumption. When you drive your car or your motorbike, you're going to be using some gallons of gasoline. And if you go from here to Houston, then you're going to use so many gallons, and the distance from College Station to Houston is going to be so much. You divide this by that, and you have your gas consumption. So the hydraulic gradient is similar to the gas consumption, but it's associated with water, because like your car, the water has energy, and it has energy because it's high on this side and low on that side. So it's forced to go in that direction. And it has energy, but it burns that energy to go through the dam, and it loses energy as it goes through. Why? Because it's hard. And in fact, there's quite a bit of friction developing between the water and the grains. And we'll see how we can calculate that force, that resistance called the seepage force. But it's that energy burning that leads to this consumption I between 2 points. So if you wanted I between point M and point N, then you'd have to find what HT at M is, what HT at N is, and then the hydraulic gradient could be calculated between the 2 points. Now, so let's go back to Darcy, because Darcy, now we have the elements to be able to talk about Darcy's law. So Darcy was a French fellow. He worked what made him famous or led to this Darcy's law is the work that he did for the city of Dijon in France. You know, the Dijon mustard, that's where the stuff is made. And Darcy's law states that the velocity, the discharge velocity, is equal to K times I. So V is discharge velocity, K is permeability of the soil, more theoretically correct would be hydraulic conductivity, it's the parallel concept to other conductivities, because flow, there are a lot of things that flow in our engineering world. For example, flow of electricity. So you'd have electrical conductivity, flow of temperature. You'd have thermal conductivity. So, but in the world of geotech, we often use the word permeability. So K, and then I is the hydraulic gradients. Now remember, the hydraulic gradient, because it's a gradient, is defined between 2 points. Now, if the 2 points are very close together, you can get an actually local value of the hydraulic gradient. So velocity, we're talking about meters per second, right? What are the units of hydraulic gradient? This is a length, this is a length, no units. So hydraulic gradient, no units. So the hydraulic conductivity is going to also be in meters per second. Now, if you keep the gradient the same, you have one dam, one water level here, one water level there, and the dam is the same height. If you make the dam out of gravel, then the K is going to be quite a bit higher, and the velocity is going to be quite a bit higher for the same hydraulic gradient. If you make the dam out of clay, the hydraulic gradient is the same, but the K is much lower, and so the velocity is going to be much lower. All right, so that's that. This permeability varies in soils. Some of the values, I would say 10 to the minus 3.
I need your consent on a few items to continue.
I don't know how to turn off that phone, okay? You win. 10 to the minus 3 meters per second to 10 to the minus 11 to 10 to the minus 11 meters per second. So it's a significant range of permeability value, and in the next lecture we will find how to measure that value of K. But what I wanted to do, at least to set up for, let's see, I only have 3 minutes. So let me talk about the seepage force, which is another, I'll do it right here. The seepage force is the force exerted by water on the soil particles. And that's the force that created the hole in the Teton Dam. You know, it was pushing, you remember the dozers wanting to backfill the hole, and then they fell in, and the water kept pushing the soil, because it was seeping through the dam and pushing the particles. So it's critically important in the world of erosion and in the proper. This force is F equals I gamma W. I is the hydraulic gradient, gamma W is the unit weight of water, and you can see that the units of this force is kilonewton per cubic meter. So this is a force per unit volume of soil. And that force, let's say that the hydraulic gradient will vary from 0.1 to 1. If you're at 1, you're starting to really ask for trouble. But let's say that it's 1, so you're talking about 10 kilonewton per cubic meter. That's 1 ton. 10 kilonewton is about 1 ton. So you're looking at 1 cubic meter of soil, and the water going through that is exerting 1 ton of force to push that block of soil downstream. So it's very sizable, and it can create a lot of trouble, as I mentioned, through erosion. So we'll stop here, and then we'll continue our discussion. We're going to discuss flow water through soil for about 3 or 4 more lectures coming up. All right, so we'll see you next time.